This video is on section 2.4 and the topic is continuity. So we've done a lot of work so far on limits and understanding limits and how to get a limit analytically, algebraically, and geometrically. So now that brings us a step farther to understand some characteristics of the function, including is the function continuous? And what does it mean to be continuous? Also, if it's not continuous, what kind of discontinuities can we expect? The limit of a function as x approaches a can often be found simply by calculating the value of the function at a, as seen down here. Essentially, that is the direct substitution method that we practiced in previous sections, where we took the limit of the x that's being approached, we put that directly into the function, and in some cases, I wouldn't say most, in some cases, an actual y value came out of the function with no issues, no indeterminate forms, no undefined stuff, and therefore that was the limit. It approached the y. If you can do direct substitution, then your function is continuous. So keep that in mind. Notice the definition. I should say it's continuous at a, at whatever that value is, not necessarily everywhere. Notice that definition 1 implicitly requires three things if f is continuous. That the y value, f of a, meaning the y value, the output, is defined. There is a y value for the x equals a. Remember, in some cases when we were talking about the limits, we were approaching a particular y value, but there may have been a hole there, and the y value point was somewhere else in the graph. That can happen, but if that does, that means we're not continuous. The limit as x approaches this value a has to exist. And not only does it have to exist, but it has to be equal to the same y value of when you direct substituted the x in. If f is defined near a, in other words, f is defined on an open interval containing the value a, except perhaps at a, we say that f is discontinuous at a or has a discontinuity at a. If f is not continuous at a. That sounds confusing as anything, which is why I'm so glad we have examples to try to visualize what this written definition means. Take a look at this example. We want to find where on this function, or in this graph, do we have discontinuities? Now, one of the easiest way when you have the graph in front of you to determine whether it's continuous is ask yourself, can I draw this graph without ever picking up my pencil? Pretty sure if you look at this graph, in order to draw it, to follow the blue lines, even at this very small point, it's a very small pick up my pencil, but I have to jump over the hole. That hole doesn't exist. So I automatically know that it's not a continuous function. Let's identify all the places where we're discontinuous. And when I ask you to identify where f is discontinuous, I'm asking you to list the x values and where you have discontinuities. So let's do that. I'm going to write in red. So I see that there is a hole here, and that happens at x equals 1. So one discontinuity is x equals 1. We have to pick up our pencil. Another discontinuity happens right here at 3, as the left limit is not matching the right limit here. Or in other words, the y value we can see looks like -1, but there is a right limit that is approaching what looks like maybe +2. Either way, in order to draw this function, I would have had to severely pick up my pencil to keep drawing. So there's a discontinuity at 3. And then the last discontinuity I see is there's a hole here with the y value in a completely different place. So if we were to take the limit as x approaches 5, we would approach the same y value. But one of the rules of continuity is that not only do you have a limit, some limit L, The L also needs to equal the Y value, and in this case, they do not. So we have a discontinuity at 5. So there's discontinuities at 1, 3, and 5 in this graph. Where are each of the following functions discontinuous? All right, well, let's look at A. In A, you could graph it because usually visuals are the easiest for students to see. Or think about what you know about characteristics of functions. This is a rational function. And when we're thinking about where is there a break in the domain, where can there be an issue, it's when there's a potential you could divide by 0. Well, that means all we care about is the denominator. And when will this denominator be 0? Well, this denominator is 0 when x equals 2, because if I substitute 2 into the denominator, lo and behold, I get 0. So this function is discontinuous at 2. There will be a hole, a missing y value. There is no output when x equals 2. So if we take a look at the B example, then we're looking at 1 over x squared if x is not equal to 0. Okay, so that alleviates the issue of potentially having a 0 in the denominator. So that's good. And then the step function says that let the function be equal to an output of 1 if x is actually equal to 0. All right. Well, let's make sure that there's no jumps, that there's no splits. So we have 1 over x squared where we're leaving out the 0. And we know that because in the graph of 1 over x squared, there should be a hole right at x equals 0. Now we just have to make sure that this output of 1 fills in the hole to make it continuous. If it doesn't, then we have a jump, or we have a removable discontinuity, and I'm going to define these in a little bit. So what we need to do is we need to find, in order to answer that question, we need to find the limit as x approaches 0 of the function 1 over x squared. If that limit is equal to 1, we're continuous because that 1 is filled in from the other function. But if that limit is anything other than 1, if it approaches any other value, then there's going to be a space between the hole in the function 1 over x squared at 0 and the actual y value at 0. So remember, how we do this is either we can graph this function, direct substitution is not going to work in this case, or we can do analytical approach by doing a table of values. So let's do a quick table of values. Remember, we have to approach from both the left and the right side to make sure they're the same. So let's throw in, we're trying to get really close to 0. So from the left side, let's do -1, -0.5, and -0.001. And again, how we're going to do this quickly is you're going to get your calculators out. In the y equals, you're going to type in the function 1 over x squared in your y equals. Hopefully you can see that. Then you are going to make sure second table set and make sure your independent variable is highlighted on ask. If I'm going too fast, just pause the video. Then go over to the table. In the table, you should see nothing in there unless you've used the table with ask feature before. And you're going to type in the x's that you want. So I'm going to type in -1. I'm going to type in -0.5. And I'm going to type in -0.001. Don't worry about my zeros that I put in there. I just had other values and I wanted to clear them out, and that was the easiest way to do it. Okay, so I'm going to write down these y values My y values are 1, 4, and then as I got really close to 0, it says 1 times 10 raised to the 6. Oh, that's a really small number. That's not 1. It says 1e6. If you remember that 1e6, so my calculator is giving me this as the answer, but that's scientific notation for 1 times 10 raised to the 6th power. Oh, so that's a really big number. So we're going to move the decimal place over 6 places, which is going to give us 1,000,000. I was thinking it's a really small number, but that wouldn't make sense because then we'd go 1, go up to 4, and then go back down. So I'm glad that I read the scientific notation, right? So we have 1, 4, and then whoa, we blow up to 1,000,000 when we get really close to 0. Let's see what happens on the other side, on the right limit, coming from the right side. Let me clear everything. No, I don't want to clear everything. So let me just hold on. Erasing takes a minute. Okay, let's follow the same procedure, but this time let's pick y values. Let's pick x values that are on the right side of our focus of 0. So +1, positive 0.05. Oh my goodness. There. Sorry for the ugly decimal point. For some reason, decimal points are so incredibly hard to write out on an iPad. And 0.001. Okay, typing that in, +1, positive 0.5, positive 0.001. Again, this is what you should be looking at in your table. So I get 1, 4, ooh, it's symmetric, and another 1e to the 6th, so another 1,000,000. Well, I think we are, ooh, I skipped a 0. I am not sure if it's 1,000,000 or if it's going to blow up more. I feel as though I haven't gotten close enough to 0 in order to determine that. So let's add one more into our table on both sides. Let's do a negative 0.00001. 4 zeros this time. Negative 0.00001. And let's also do a positive 0.00001. Ooh, that brings it up to 1e10, which means 1 times 10 raised to the 10th power. So that's 10 zeros after. That's a ginormous number. I think it is safe to say that this function, 1 over x squared, is approaching infinity, a really big number, which we're actually going to cover in a different video of infinite limits. If we take a look at the graph, so it's already in your y equals, so just hit graph. We're looking at this as our graph. Notice that as we approach 0, the function is going straight up. X equals 0 is an asymptote. So this function has a discontinuity at 0. Okay, so x equals 0 is the discontinuity for b. Let's erase all the annotations. Let's do C now. So knowing that this value was our issue in the last problem, there's probably a good chance that that's the same place that it's discontinuous for this one. But again, I want to make sure. So I'm going to graph this function and see what happens as I approach 2 and see if it's something obvious. If it's obvious, like it's approaching an infinity, well, then there's my answer. There's a discontinuity at 2. So again, I'm going to go into my calculator. I'm going to go to my y equals. I'm going to type in parentheses x squared minus x minus 2, close parentheses, divided by, open parentheses, x minus 2. Remember, we got to tell the calculator where the groups are and when order of operations. Hit graph. Ooh. So I hit graph this time. I'm gonna zoom in. And when my function is approaching 2, ooh, hold on. I just have to change my window real quick because I'm missing what I really want to focus on. This is what the graph looks like. I'm not seeing a strange behavior happening at 2. In fact, if I was just looking at the graph, I'm almost tempted to say that it's just a line. Well, why is that? There's a very good chance. Now, I can see by the denominator that we clearly have a problem at 2, but it seems as though it might just be a hole. Is that hole, though, at 1? If the hole is at the y value of 1, we're good to go. Now I'm looking back at my graph and it's not looking like it. It's looking like as x approaches 2, y approaches 2, which means that there's a hole in the function. Let me show you. Hard to see on your calculator because a hole in the calculator is 1 pixel. That's not very easy to see as the naked eye. Say this is the graph I'm looking at. Okay, visually, it looks like a solid line. But I already know with my algebra that there's a hole or there's an asymptote at 2 because that would cause a 0 in the denominator. Now, if this hole right here was at positive 1, so that this positive 1 y value would fill in the hole, then we wouldn't be discontinuous. But the problem is it doesn't look like that. In fact, the graph actually goes through 1 on the x-axis. So that means that if I was to draw the step function, my y value, I don't know what just happened to my axis. Here we go. My y value at x equals 2 is at 1. And that's why we have a discontinuity at 2, because there's a removable discontinuity. Picture like a piece being taken out and put somewhere else. Now, part D is a totally different function. Don't worry about that function. Let's not cover that today. It doesn't come up again, so you don't have to worry about that one. It is in the original PowerPoint that's posted in our course, though, with all the solutions. I just took them out because I didn't need them when I was lecturing. Show the graphs. Okay, so these are the graphs of the function. This is the one that I skipped. It's a popular step function, but it's called the integer function. But we don't need to cover it today, but it clearly has discontinuities at every integer. So here we noticed that there was a hole, and it was literally a hole, not removable because there is no y value whatsoever for this function at 2. Here we have a y value at 1, but the limit goes to infinity. Here we have a hole, but it's removable because there actually is a y value. We've created a step function. And this one is a very classic step function called the integer function, which essentially has a flat horizontal line between every integer, equal on one side, open on the other. So it's a function. It passes the vertical line test, but there's a ton of jumps. So jumps is when you have to stop, whoop, pick up, and go to the next one. In each case, the graph can't be drawn without lifting the pen, meaning it is not continuous. The kind of discontinuity illustrated in parts A and C are removable because there's a hole and there's a removable piece. Although I wouldn't call A removable, I would just call it a hole because there is no actual y value somewhere else, but it can still be called removable because maybe it was removed and thrown out. Now you don't have it. So removable on A and C. And then discontinuity for B is called an infinite discontinuity because you have a piece that went up to infinity. And in part D was called a jump because you had a hole and you had a jump to the removed piece. No, B was not that one. That one was removable. Jump discontinuity. B, what was that? Sorry. D. D. I said it was jump. 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 So these are jumps. This right here is infinite because of the infinite piece. I call that one a hole, but it's also referred to as removable, just the removable piece is missing. And here we have a hole with a removable. So a function f is continuous from the right at a number at a value a if the limit as x approaches a from the right side of the function is equal to the y value. And f is continuous from the left at a if the same is true. A function is continuous on an interval, just straight continuous without direction given, if the left limit matches the right limit. And that specific limit is also equal to the y value. If f and g are continuous at a and c is a constant, then the following functions are also continuous at a. Okay, so that's just a general rule of thumb. Essentially, your basic polynomials and your rational function where the denominator can't be 0 are continuous, as long as they follow these rules, by the way. Okay, so polynomials, root functions, exponential functions, rational functions, trigonometric functions, logarithmic functions, they have continuous domains. Find the interval on which I should be more specific, they have continuous domains at a specific value. So there are some exceptions with rational functions, though, however, and some trig functions. So this theorem is a little questionable. I feel like I'm missing something in that theorem because that's not particularly true. Think about the tangent function. The tangent function has asymptotes at pi over 2, and the rational function, whatever the number is in the denominator that makes it 0, is an asymptote as well. So that's not necessarily true. I should probably delete that slide. Find the intervals on which the function is continuous. So, I mean, this one is fairly straightforward. This one, we have a denominator here, and this denominator, we can see where the problem would be. If x equals 2, then we have a 0 in the denominator, and that's undefined. And we know from our algebra days that that would mean there's an asymptote at 2. So where are we continuous? Remember, if I was just listing discontinuity, I would just say x equals 2. But if we wanted to write the intervals of the continuous domain, then we just have to write it so that we leave out 2 and not include it. So that means negative infinity. You know what? That's what the last slide was talking about. It was talking about that when to identify where the undefined piece is in those functions, it's continuous everywhere else. It was just worded wrong. That makes a lot more sense. So here our discontinuity is at 2 because the 2 is what gives us an undefined in the denominator. So we have negative infinity to 2. And then we'll pick up again, union, 2 to positive infinity. Remember that curved brackets mean not equal to in interval notation. Square brackets mean equal to in interval notation. So if I wanted to say I'm including 2, then I would use a square bracket. But if I specifically just want to leave out that one value, I use curved brackets. You don't want to say negative infinity to 1 union 3 to positive infinity because you're leaving out more than just the value of 2. We're working with the real number line here. So you're leaving out infinitely many decimals between 1 and 2 and 3. And you don't want to do those because those don't cause a problem. So I'm talking about 2.5, which is between 2 and 3. That would be missing if you literally didn't write the 2. So curved brackets is literally indicating that the exact value of 2 and only 2 is being left out in order for this function to be continuous. Last example for this section, what c makes the function continuous everywhere? Okay, well, let's think about this. Look at where the break is. So I'm looking at this function, and I see that it uses 4x plus c up into and including the value 3 on the x-axis. So it's from the left, from negative infinity all the way to 3. We're using 4x plus c. And then right after 3, the infinitely small decimal after 3, so 3.0000000000000000001. Beyond, we are going to use the CX after that. So the break between when we use one function over the other is happening at the value 3. Now we need a C that will make this function continuous. Now recall other step functions that we've seen in this section. When step functions were not continuous, it's because where one function left off, the other one started in another place. So we want 4x plus c to meet up with cx at the exact same spot, and that spot is x equals 3. So how the heck do we do the algebra for that? Well, let's literally write what we just visualized into an algebraic equation. We want 4x plus c to be in the same place when it meets cx. So where does 4x plus c meet cx? Well, let's move this. Let's move this cx onto the other side. Oh, you know what? That's a lot more work than I want to do. Why don't we just move the other x one onto the other side? Let's do that instead. We want the x's on one side and the constant term that's all by itself. So let's actually subtract 4x on both sides. So we get c is equal to cx minus 4x. Then, oh, scratch that. Start over. The reason why that isn't going to work is because we're not solving for x, and I put the x terms on the same side, and we're solving for c. We want to know what c is. So you want to get your c terms on the same side in order for us to be able to solve for that. It's always good for me to make as many mistakes when I'm lecturing, because then you see that I'm also human and you also know why it was a mistake, so you won't make it yourself. Let's subtract c on both sides. So we get 4x is equal to cx minus c. Let's factor out this c. So that gives us 4x is equal to c times x minus 1. And let's solve for c. So in order to solve for c, we are going to divide both sides by x minus 1. Let me clear out this stuff so I have more room. So that gives me, okay, again, the last step we left off on was 4x is equal to c times x minus 1. We're going to divide by x minus 1 on both sides, so we get c is equal to 4x divided by x minus 1. Now we want to find c at the exact break in the step function. So we're trying to find c when x equals 3. So let's take 3 and substitute it in for every x. So that gives us 4 times 3 over 3 minus 1. We get 12 over 2. And we get that if we want this function to be continuous everywhere, and we know a step function breaks at 3, then the c needs to be 6 in order for the 4x plus 6 to intersect with 6x at the exact same y value where x equals 3. All right, that concludes our continuity lesson for today. I'll see you next time.